Okay, welcome everybody. This is the first colloquium in spring, correct? And today is my pleasure to introduce you Dr. Constantinos Kolias, Kostas, and he is associate professor at University of Idaho, and his expertise is in cybersecurity and privacy for IoT and cyber infrastructure.
Yes.
And
Thank you so much for inviting me. And today's discussion, I hope, yes, I hope some of you have the experience and expertise, some expertise regarding analysis, data analysis, machine learning, maybe cybersecurity, but certainly computing in general, because what I'm going to talk about is one of these things that people always neglect, even cybersecurity experts neglect, but this day and age, it has gotten so severe, the attacks that we experience from this surface, that we cannot neglect it anymore. And this is side channel analysis. I'm sure that most of you do not know the term. So I'm going to describe exactly what side channel analysis is all about with a little bit of life. So I want opinions. What are these guys doing? What do you think? They're fighting, for sure. They are fighting. They're fighting. Why? For what reason?
Over disagreement.
Yeah, they disagree. For sure, they are frustrated. We cannot know for sure why they are fighting. We cannot hear them, right? Their primary way of communication is voice, sounds, but we do not have this luxury. We do not have the primary means of communication. We do not have access to that channel of information. So we need to infer. And when we need to infer something, we cannot be 100% accurate. So I do some lip reading here. Child, school. What are they fighting for now with this extra piece of information? Maybe someone forgot to pick up the kid from school. Yeah, that's a nice topic of gossip, especially if you are in the neighborhood. But today's discussion is not going to be about gossip. It's going to be the use of these involuntary means of communicating valuable information for purposes of war, and more specifically, cyber war, cybersecurity. The first use of side channel analysis was World War II, where ingenious German scientists were able to infer the weather conditions in London just by the sound of the ding-dongs of the Big Ben when it was broadcast from the BBC News. So imagine that, figuring out whether your airplanes should strike London based on a radio station broadcast thing. So yeah, every hour the BBC News was broadcasting the sound of the Big Ben, and that's how German Luftwaffe knew exactly what's the weather conditions in London. That's the first documented case of side channel analysis for purposes of war. Today, we have access to better equipment, better strategies, better analysis methods, and also machine learning and all this type of stuff. Artificial intelligence are at their peak right now. So we have our artillery is much better. In fact, not long ago, scientists were able to crack passwords and infer text that we are writing, we are inputting on our computers by just typing the keystrokes of the keyboards. Another case, scientists were able to infer speech inside a room from the next building by what? Monitoring the vibrations of light bulbs. Very serious and interesting research was conducted by researchers from NYU, where they were able to transform an HDD, a hard drive, the analog hard drive, not the solid state, into a microphone, a high precision microphone, by monitoring and analyzing the vibrations of this arm that you see there, which is so sensitive that if you speak inside the same room as the HDD, this arm will vibrate just a little bit, enough to figure out what you're talking about. Oh, very interesting things. All of these were cases, offensive cases, where we use side channel analysis for attacks, for compromising things. What about defenses? Well, in this case, you probably know exactly what I'm talking about. This is what? How do you call that? Hologram. Yes. Not very precise. A lot of discussion in the topic. However, the intention is the same. Analyze not the primary means of communication, like the voice, which can be manipulated by the user, in a sense, that guy to lie, but rather unintentional means of communication, such as the reaction of the body in certain stimuli. You can see the pupils dilating, you can see hair raising when someone is lying, or there is a certain reaction, physical reaction, that cannot be easily manipulated when someone is lying. And this is basically the theoretical foundations of the lie detectors that we know right now. So this is a case of employing side channel analysis for defensive purposes. And of course, today we care more about what? Digital devices. The same principles can be applied in the realm of digital devices. To do what? Both for offensive purposes, let's say cracking cryptographic keys from cryptographic libraries, by analyzing things like, for example, power consumption patterns, or the electromagnetic emanations from the CPU, the involuntary electromagnetic emanations, not the primary means of communication, not the Bluetooth or the Wi-Fi signals that get emanated from network cards, but rather the signals that get emanated from components of the CPU or the board in general during its normal execution. So by capturing and analyzing these signals, analog signals in this case, you can infer some information, and by employing probability, statistics, and things like that, you can extract valuable information. Again, the theoretical foundations of all of these principles lie in the fact that every time an instruction gets executed inside the CPU, it consumes certain amount of current. Not exactly the same for each instruction, and I'm talking about assembly instructions at this point, right? So you have a C program, you click compile, behind the scenes, the program gets compiled into assembly, machine code, and so on and so forth. These type of instructions get fed to the CPU, and this is what gets executed inside the CPU, not the C functions themselves, not the C statements themselves, but rather the assembly code that corresponds to this type of functionality. So for each one of these instructions, we have observed that different amount of current is drawn to do certain things, feed the register with more energy so they can store some information, or put more energy in a capacitor, load the capacitor, or discharge a capacitor, or something like that. So for this reason, and due to these changes in the flow of the current, we have the formation of electromagnetic signals or other types of signal, acoustic signals, in some cases, thermal signals as well. And by capturing these signals and analyzing the differences, we can do correlations, we can do assumptions, and we can say, you know what? Most probably right now, what is being executed inside your CPU is this and not that, which gives a very good information about the type of things that we. So what does that allow us to do? First of all, like I said, for offensive purposes, maybe crack cryptographic keys. You know, if an if statement gets executed when it's time to produce a key, as opposed to an else statement, then we most probably can reliably identify that. What else? Still on the offensive side, lately, the new trend is to reverse engineer neural networks. You know, a lot of energy and a lot of data is required to train neural networks, right? However, these models are supposed to be not very explainable themselves. You cannot reverse engineer just by observing the weights and say, okay, you know, the data that corresponds to this model is this, and I don't need to waste energy right now. So a lot of people, by doing side channel analysis, by analyzing the electromagnetic emanations that are created during, you know, the inference stage, for example, are able to reverse engineer the weights and the structure of neural networks so that we don't need to train at all. We can have the neural network pre-trained and no one will know that we did this illegal reverse engineering thing. On the defensive side, I talked about knowing exactly what type of instructions are being executed inside the CPU. What could we do on the defensive side with this type of knowledge? What could we do? Well, malware, when malware installed and is executed inside the CPU, it alters essentially the structure and the sequence of normal sequence of instructions that should be executed, right? We have a program, it has a vulnerability, let's say a buffer overflow thing. It allows an attacker to install extra malicious set of instructions, extra code. It used to be 1, 2, 3 instructions. Now it's 1, 2, 3 plus malicious 1, malicious 2, malicious 3. This change can allow us potentially to create totally external, passive, antivirus system by just monitoring the electromagnetic emanations from the CPU. And this is basically going to be the topic of this discussion. We don't care too much as a group for the offensive side of things, but rather the defensive side of things. But I'll give you an example of how things work. So you see code that is executed on the right. It's C code that is executed inside an Arduino device. Very simple CPU architecture. No great fancy micro-architectural features, no speculative execution, no cache misses, nothing like that. Simple fetch and execute type of pipeline. And when this program is executed inside the loop, as we see there, what we see is the number of peaks. These peaks are indicative of an I/O operation that happens in memory. Typically, I/O, especially when it comes to memory, they draw a lot of current, so a lot very powerful, relatively powerful EM signals are being generated, right? So notice the peaks, please. It's 1, 2, 3, 4, 15, and also notice inside the loop the number of iterations that are dictated in that loop. Immediately, And without being experts in the area, we can identify what the number of iterations, the number of executions that happen inside this loop, right? Inside this segment of code. So with a little bit more experience, we could potentially even understand exactly what's going on, what type of I/O operation happens inside the CPU. But still, I think you get the point, what side channel analysis is all about. So let's see how we can use that set of methods and principles for doing anomaly detection for critical, inside critical infrastructures or embedded devices inside critical infrastructures, and why it makes sense to do that. So we have critical infrastructures or industrial systems, and the first thing you will hear is the IT and OT. IT is the traditional IT networks full of computer, desktops, laptops, and this type of stuff. While the OT networks are traditionally what, the sensors, the PLCs, SCADA systems, and pretty much what controls and comes very close contact with the physical environment, right? So there we have the cyber physical systems, again, the PLCs, PGAs, and all this type of stuff. So the OT component, the OT network used to be very isolated from the external world, siloed in a sense. Nothing could go in easily, nothing could come out easily. PLCs that were meant to control a physical process very, very well, but without communicating, without connected to the internet, without communicating their information to the outside world. But today, we have these things called the IIoT, industrial IoT, where we have the convergence of the IT world and the OT world through these bridges of these cyber physical components. And these are the things that expose the traditionally air-gapped environments to the outside world and the dangers of the internet and all this stuff. So what I'm saying, what I'm getting at is it's so easy, so much easier today than any other time to hack into cyber physical systems. And I'll ask the audience, what do you think that compromising cyber physical systems and industrial processes could, what's the outcome? What's a possibility you think that could happen?
Mass power outages, the grid were attacked.
Sure.
Or like infrastructurally, like the banking financial system, there's all kinds of pieces there.
Yeah, what else?
Attacking water systems.
Water systems with, what's the impact? What's the outcome?
They could just put less of the purifying chemicals in or more, and it would become toxic.
Toxic. So people would die. In almost every situation that you can think that involves cyber physical systems inside critical infrastructure, people die. That's the outcome. Catastrophic events. And that's an awesome way to do terrorism as well, right? Kill people. It's nice. People get the message right away. So yeah, I mean, it's not nice as is, but people get it. Yeah. So these things, however, do not have dedicated antivirus, anti-malware systems. No, nothing like that. Why? Because they are weak. Because they do not have advanced CPUs, they do not have a lot of RAM, they do not have a lot of resources, right? We are talking about stripped down devices that are meant to perform one operation well, and that's it. They are not meant to communicate with people, they are not meant to provide nice user interfaces and fancy graphics and all this type of stuff. No, nothing like that. Just be there steadily, no matter what, execute the physical process, and that's it. So, again, awesome area for someone to attack. This is an example of this type of cyber physical systems. It's called PLC, Programmable Logic Controller. These are the types that empower water treatment facilities, nuclear power plants, nuclear purification plants, and things like that. They control, for example, the frequency that a rotor rotates. They control the opening and closing of valves and things like that. Very simple operations, but they have to do that very reliably and efficiently over and over again for a prolonged period of time. Sometimes, almost always, without updates for 30 years or more. Keep that in mind. So, again, CPUs, RAM, memory, what are they? Yes, they are digital devices. They are yet another computer inside a network. Sure, up to now, a little bit more secure network, a little bit more isolated, but still a computer inside a network that can be hacked, as incidents like Stuxnet showed us. And relatively easily, they can be transformed into a threat, into a cyber weapon, the target of state actors and the evildoers. And as we discussed before, yeah, sure, we are talking at this point about massively terrorist incidents, mass attacks. We are talking about loss of human lives, destruction of the environment. Also, we are talking about economic attacks. For example, shutting down a nuclear reactor may inflict an additional cost of $2 million per day. So just by the threat of this thing is out there, and something could go wrong, and oh my God, something appears to be happening, but I'm not sure. Let me shut down the nuclear reactor. $2 million just from the threat, not from the indication or then the conviction that we are infected. No, nothing like that. So we try to emulate inside the PLC what a PLC would do when it would operate normally to purify gas, and how the electromagnetic operations, the signals corresponding to theoretically the same operations look like after the infection with Stuxnet. And you can see, even with the naked eye, that the patterns are clear. The patterns do not match. On the left, we have the normal execution. On the right, the execution after the infection. It was the exact same model as Siemens S7 PLC that was infected by Stuxnet. So these are the emanations that you get when you put an electromagnetic probe, an antenna, on top of the CPU of the PLC. Okay, and I guess the difference is loud and clear. We don't need to employ any type of anomaly detection, sophisticated malware analysis algorithms. Even with naked eye, we can see that something is off. All right, so awesome so far. It seems that we have found something that is very interesting for us. Maybe we have discovered the perfect antivirus system for this type of devices. Am I correct? I guess not. There are several advantages. For example, we do not require a dedicated software to be installed on these PLCs. So very, let's say, subtle, very inoffensive way of protecting the system, for sure. We can treat the PLC as a black box, right? We do not know exactly what it's doing inside, but if we observe for a long period of time, we could gather patterns. And if the patterns match, it's business as usual, right? We can also detect, as we will experimentally show, even subtle variations of the software. If you even install one extra assembly instruction, and usually malware installs much more extensive malicious code, much larger, then we are still going to be able to tell. And also, underline that, it's very important, we can detect even zero-day attacks. Two questions: what are zero-day attacks, and why I can detect zero-day attacks with this method? What do you think, guys? What are zero-day attacks first? Yeah,
It's an attack that there's no known defense for. First time it's been seen.
sure. Because most probably it was released, I don't know, yesterday or a month ago, and people are still trying to analyze what's going on and figure out maybe a defense. That's a zero-day attack, sure. And why this side channel analysis thing is good for detecting zero-day attacks? What's the methodology? What could it be?
Just the ability to catch that anomalous behavior.
Yeah.
Get a baseline.
Yeah, exactly. So you nailed it. You said two words: baseline, and then anomalous behavior, like deviation from this baseline. So if I monitor a system and I figure out that this is the normal behavior, and it's relatively easy in this domain. Remember, PLCs and cyber-physical systems do things continuously all the time in the same way over and over again. So it's easy for me to create a baseline what is considered normal behavior. And that any deviation from this notion of normalcy, whether it is EM signals or power consumption or acoustic signals or thermal behavior, I could say that something is not necessarily a zero-day attack, not necessarily something that reliably I can tell Stuxnet versus whatever, right? But for sure, something is off. And indirectly, via this strategy, I can even detect zero-day attacks, right? All right. And at this point, let's just mention why it really makes sense. This type of approaches make sense inside the embedded system realm as opposed to higher end realm. Higher end realm, servers, desktops, laptops, smartphones. What do they have in common? They have advanced, very sophisticated type of CPUs, multi-core systems, running stuff in multiple threads in parallel or concurrent execution. So it's a little bit tricky for me because when I see something happening inside the CPU, I'm not sure exactly whether it corresponds to something that I'm interested in, or let's say a GUI that is executed, a graphical user interface that is executed in parallel at the same time as the process that I'm interested in. All right. Do you know what it means, like the parallel execution or concurrent execution in this type of CPUs? What it means? How it works? Yes. So basically, there are no. If we are not talking about multi-core systems, we are not talking about real parallelism here. It's 2 or 3 processes or 10 processes or 1,000 processes running at the same time, by means of stopping the execution of one and starting the execution of another in various time slots. That's how it works. Of course, in multi-core systems, it doesn't work exactly like that, but you get the picture. So things in the high-end realm, high-end server systems realm, are complicated. But here, in the embedded system realm, things are easy. Very simple programs running the same things over and over again with minimal user input, and user/human input is a little bit unpredictable. I don't know if the user is going to put $1,000 or $10 or $1 million at any given point in time. But I can predict whether PLC that is connected to a thermal sensor is going to generate temperatures from -1 to 100 degrees, more or less. I can predict that. So what I'm getting at is much simpler things, both in terms of hardware as well as software in the embedded system realm. Okay, much easier to fingerprint. So yeah, it makes sense. And if you have a strategy like what we discussed previously, where we capture the signals and the signals are never going to look 100% exactly the same. We have things that happening at the hardware level, random things happening, and we have things happening at the environment level, like noise, environmental noise, interference from other devices, all this stuff. So never 100% the same. But if we capture a database of signals, several thousands of signals, we can statistically infer the normalcy, what is known as the baseline, the threshold between what has been seen before and what is perceived as normal, as opposed to something that is drastically different, which points to the direction that something has been altered, either in hardware or software level. Okay. However, things are not perfect, obviously. There are a huge number of challenges, and I just picked two because it's going to be more obvious to you. The signal acquisition phase. We said that we have phase number one, where you do the fingerprinting. You collect all the signals and you draw the baseline. Then during the deployment stage, you get a new signal. You don't know whether the signal is normal or anomalous, but if it fits inside the baseline, then it's normal. If it's outside the baseline, then it's anomalous. However, step number one is the signal acquisition. Ask my students, they will tell you that they hate this stage. They have to go to the lab, use a dedicated equipment, collect the signals. Sometimes they are a little bit off. I get mad, I yell at them, they go back, they capture again, still not perfect, and so on and so forth. So very time consuming, error prone, and specialized. It requires even specialized personnel to know exactly how to capture these signals. Because if I put the electromagnetic probe here as opposed to there, two totally different signals. They may have some resemblance, but they are going to look different. And if from training stage to deployment stage, I also move the probe around, two different things. You will get the impression that, oh my God, I'm just deployed that thing and I'm already hacked. No, a dog moved the probe a little bit, something like that. So again, error prone, very costly because of the time that it requires to capture all these signals. Also, dedicated equipment. The oscilloscopes are not cheap, and especially the oscilloscopes that capture at this frame rate, these frequencies, not very cheap also as well. But apart from that, apart from the signal acquisition stage, we also have an additional challenge. Environmental noise, as I said, someone open their, microwave, and you get a lot of noise. Someone, conditions change in general. Like I said, you can move the probe around, totally different signal. So yeah, challenges. While this thing, side channel analysis for defense purposes, works great in theory and inside laboratory, controlled laboratory environments, I see it's very difficult to deploy that thing in real life at this point in time. So what can we do? And this is where I will focus this discussion on the first challenge, that is the signal acquisition. And this is where the generative methods, machine learning, generative adversarial networks will come into play to help us a little bit. So the main hypothesis is that I have a program and I see that program has some basic building blocks, whatever that is, that get repeated over and over again. For example, if I have a function that has 5 lines of code and I call this function 10 times, this is a basic block that gets repeated 10 times, the function, the internal stuff inside the function. Other basic building blocks could be, I don't know, if the contents of an if statement, and the contents of an else statement, the contents inside the loop, the contents of whatever, even down to the point of isolated assembly instructions. This is the lowest I can go. All right, so my main hypothesis is that if I fingerprint these basic building blocks, could I potentially be able to see a program as is, as text, let's say, and infer somehow, based on what I know, infer how this program would look like, the EM emanations of this program would look like, so I can tell whether, when it's deployed, whether it is infected or not, without going inside the lab and capturing signals for training. In other words, is it possible for me that I have created a database full of associations of building blocks, let's say assembly instructions, and their electromagnetic fingerprint, and then I receive the executable, and just from the executable, I imagine what I will get during deployment time. So this is our hypothesis. Yes, you can do that, but in reality, nothing is so simple. And one simple project turned out to be a very laborious and a very intense process for us. So step number 1, observation number 1. We saw that, yes, in theory, you can say, oh, I have this add instruction, or I have this move instruction, or I have this jump instruction. And I collect it in isolation in between, let's say, no ops over and over again. And I grab that signal, that fingerprint, and I put that on my database. I'm not done, because in practice, if that jump instruction is preceded by a no op, as opposed to an add, as opposed to whatever, it will look totally different. So I need to do a better job harvesting instructions from different places, and that's going to transform a relatively straightforward and easy fingerprinting or creating a database job to something that is almost impossible for me. It doesn't make sense for me to capture. So what I'm saying is that, no, you cannot put isolated instructions and their corresponding signal associations inside the database. What you need to do is most probably have this instruction here. Give me a second. You can have this instruction here preceded by a different instruction, this instruction preceded by another instruction, and so on and so forth. This is what we chose to do. And we saw an improvement. We saw that it is possible to grab these things and, yes, stitch that, follow a concatenated approach and create the output, an imaginary synthetically generated output manually. As a second step, we took this database of signals or basic building blocks, and we fed that into a basic GAN, generative adversarial network. And it produced a theoretical synthetic representation of that signal. And we tried to compare. And as you can see, the success is very, very good. This is the residual gas method. And excuse me for that. Suspect this. And yeah, so this is the output of GANs. We took a program in its text form, assembly instructions, and we told the GAN, this is the program that we would like to generate. What are the corresponding electromagnetic signals for this program? And you see the blue one is the real program that was captured from in the field from an antenna, and the dotted orange line is the synthetically generated. What counts in these cases is not so much the morphology of the actual signals, but rather the amplitude. These signals are amplitude modulated, meaning that really the peak, the amplitude of the signals is what counts most. And in this case, you see very close resemblance of especially the amplitude, but I would go one step further and say even the morphology of the signals is very, very close. We have some misses here and there, I don't know, but generally we are safe. It's very, very close. And this is when the GAN has been trained into 100% of the instructions that we'll see in the program that we are going to ask it to generate. Because we also asked it for a case, we created an incomplete database, of course, because it's so hard to create an exhaustive database comprising of all possible combinations of instructions. And we said, you know what? Yes, I understand it's a possibility that you have not seen these instructions, do your best thing. And the GAN was trained on, in this case, in the second case, in 60% of the instructions that observed in the program that we asked it to generate. And still, with some exceptions, more exceptions this time, still it did a good job. We have a phenomenon called time drift. You can see that the signals start to drift from the normal cycles. Cycles are fixed and their duration is fixed. However, these signals start drifting a little bit. Still, overall, they show a good behavior, even with just 60% of the cases that we are feeding the GAN, the instructions that we are feeding the GAN being observed in the training set. Now, because we observed this problem, and because the signals we know that are amplitude modulated, meaning that we care more about the amplitude of the signals, we did this weird feature engineering thing. We extracted the amplitude of the signals and we hold just the amplitude, nothing more. And we see still that it's clear that most of the stuff, especially in the first case, are so close to the real signal. In the second case, yes, they are very close, not that close as the first case. And we said what type of similarity we have. We trained the different types of GANs, residual GANs, transformer GANs, and diffusion GANs. And we said, okay, what's best? And do we get something that is very, very close to the real thing for the full signals and for when we are training the GAN in the peaks only? And in this case, we saw that the artificial signals that are produced from the res GAN is so close to the real signals. We compared that with Euclidean distance as the dissimilarity metric, and it was so close that yes, in almost all cases, except maybe for the 60% thing, we were close to the real predictions. The same thing with the peaks. Actually, the peaks were even better They did even better in most cases, and actually all cases. Even 60%, we have much closer similarity, especially for the rest GANs, that we say that what is produced really approximates the real signal. So yes, some things about the time. Generally, we are talking about very efficiently. It's very efficient to train these things. And now to the good part, we did that synthetic generation thing for training anomaly detection algorithms with synthetic signals as opposed to real signals. So we took this process out of the lab and we put that process inside the computer. Basically, that's what we did. From now on, we said, okay, you're not going to have to capture signals. And then what we did, we deployed the system and we asked it, okay, is it infected? Is it infected? All the time. And we saw that basically these are the signals of the real versus the real. And these are the signals, the generated versus the real. And these are the signals of the malicious. We have two different programs. The malicious, which is easy to detect, a lot of code has changed, and a malicious, which is hard to detect because just one or two instructions were embedded by the malware. And in both cases, we see that there is a huge difference. There is a very clear separation of the distributions of synthetic against real baselines versus real normal baselines against the malicious and the malicious. A clear separation here tells us that it's going to be so easy for an anomaly detection method to be able to reliably infer real, detect real versus anomalous. And as a matter of fact, that's how it is. We get a basic anomaly detection algorithm based on autoencoders, and it was trained with synthetic signals. And then we tested that. And the AUC scores that you see, these two are for the easy and the hard case when it's full signals, and these two are the easy and the hard case when we are talking about peaks. You see that the AUC score is perfect for both the easy and the hard cases. Obviously, this was expected, again, because we have totally clear separation between the classes. Now, our next work is, okay, you have found an reliably way of generating high fidelity synthetic signals that can be used great for anomaly detection purposes. But can you do better? And especially, can you do better when you want to target things outside anomaly detection? And we say, yes. You know why? Because so far we were feeding instructions, just instructions. Can we feed more? And why would we feed more? Because we have identified that it's not only about instructions, it's also the entire state of the board, the load of the capacitors, the values of registers, and things like that. So if we also reliably extract this information from the board and feed it to the GAN as well as the instructions, we could more reliably train the GAN to figure out what's next. What's the signal for this corresponding piece of code when the state of the board is like this is going to look like. Again, an add will look differently than when the state of the registers is all zeros. And the execution of an add instruction when the state of the registers are all, let's say, 100 or something like that. So this is what we get. And it may look a little bit misleading, may look like it's crap, but it's not that crap. Because if you really analyze that, you will see that even the morphology of the signals, the peaks here, look at that. how the peaks resemble and also the valleys resemble the real signal. Yes, we have still this drift issue, but we can synchronize the signals again. We can use dynamic time warping, and we can do feature engineering. So it's not a huge problem. In this case, I want to insist that feeding more information regarding the state of the board can lead to almost 100% fidelity between the real and the generated signals. And where does that lead us? It leads us to things outside the scope of anomaly detection. It leads us to possibly reliably doing something like that, have a cryptographic algorithm that is supposed to generate or consume to use a key, a cryptographic key, and analyze the decisions that the algorithm is doing reliably and inexpensively and offline without us being in the lab at all, be able to generate and tell us, oh, you know what, mister? You have a bug in your new cryptographic algorithm that leads to the leakage of information, which leads to the inference of a cryptographic key. And that's going to be awesome in the near future, because like I said, you don't need to step foot in a laboratory environment and capture signals over and over again and hate your life and come to your supervisor crying and say that you want to quit and things like that that are not very productive at this point. Okay, so yeah, this is the idea behind our work. And at this point, I'm free to get questions. Yes.
I'm curious, like, how you have trained your, again, the RDS scan or again, you have shown. So is it, what type of data is like, did you train with it only signals and assembly course altogether?
Yeah, so two different strategies. In the first case that I saw here, we trained the GAN just with this. We have sequences of instructions like text, basically. The inspiration is text to speech synthesis. We give a GAN text and it produces synthetic speech. That's our inspiration. And we said, can we do the same for code to signal synthesis? And this, instead of words, yes, we give instructions. And this is the corresponding real, we have captured that in reality, corresponding real signal. For this sequence, for that sequence, for that sequence, for that sequence. Obviously, this is not easy. We do not claim that even that this database is exhaustive. We have tried to replicate things that actually exist in the database, but a company potentially could afford to do this type of fingerprinting and create a holistic database. So this is approach number one that we do here. And the second approach is pretty much this, plus, except from this, an array full of the values of the registers. That at that point, the values that the register have at that point in time, and the corresponding signal as well.
So the resultant it is generating the signal measures and when you are just measuring the similarities with the generated signals and the original signal. So what type of similarity score you have used? What type of evaluation metric you have used?
The similarity metric is simple Euclidean distance.
Mhm.
And generally it's fine because our signals were not that huge. Yes, if we had 100,000 signals, yes, it would be, maybe that would not be very efficient. At the level that we, the length of the signals that we care about, a simple Euclidean distance gave us the dissimilarity or the similarity.
Yeah, because in computer vision, FID, fetches inception distance or inception stories, traditional or classic metrics that used to get the similarities between the generated images and the original images. So yeah, I got my answer. Thank you.
Firstly, thank you for this presentation. It was wonderful. I wanted to ask, like, do you see this technology being used to generate more synthetic data that are like closer to the real ones? Because we are always in shortage of data.
Yes, and that's the motivation behind our work. We are in shortage of data, especially when it comes to cybersecurity, not only side channel, anything related to cybersecurity, we are in shortage of data. And, people in medicine used to complain about the same thing. People that were doing anomaly detection or, AI-based methods in medicine, they used to complain about the same thing. But, these fields are fundamentally different in terms of their economics. Because, you can throw $1 billion in medicine and nobody will say nothing. But if you throw $1 million in cybersecurity, a lot of people will object and they will say that this should go to marketing instead, as opposed to security. So yeah, we have lack of data and we cannot do anything about that. So right now, the road ahead is produce data very, very inexpensively so you can train algorithms efficiently. These LLMs cost kind of like, I don't know, the cost of energy to power New York for 1 month. I don't know, that's something that is astronomically large. In cybersecurity, you are never going to see that type of investment. If you can see that, it will be retroactive after the incident, not proactive. Yeah. So yeah, I strongly believe that these type of methods and artificially, synthetically generating data is the road ahead. One student from my group is trying to do something very interesting. He's trying to train LLMs that will produce synthetic pickups. Pickups is the format for Wireshark, like network traffic, by giving a description of the attack. So, you have heartbleed. How does heartbleed works? Oh, that way and that way and that way. Okay, so what's your normal data that are produced? What's your normal traffic that is produced in your network? This. Okay, with this, plus the description of how heartbleed attack works, I will produce and will inject anomalous packets that should resemble the packets that are produced during a heartbleed attack.
Yeah. So if that comes out, that literally solves a lot of data issues.
Yes, it's not easy though. It's not easy, but for sure, what I'm saying, synthetic generation of data is the solution for a lot of problems. And we see that happening very quickly. I see that LLMs and all this stuff have been trained also, apart from real data, also with synthetic data. And they are trained very efficiently.
Thank you.
Yeah.
Thank you.
Okay, thanks. How much would it help to have a higher spatial, temporal resolution, like on actual measurements is good, but like how much would it help to have a high spatial resolution as well?
Explain spatial.
Like as in if you're, like you're taking some electromagnetic signal as a specific location, away from a chip and, or sometimes they're just taking measurements directly on a wire or whatever. But if you had like a, electromagnetic microscope and things like that.
It will help tremendously in terms of transferability and generalization of these type of approaches.
Mhm.
But what we have seen in practice is that as soon as you port these approaches outside the lab, that is a control environment, they all suck.
Yeah.
So by feeding with what you said, pretty much more cases of the same thing from different perspectives, spatial as well as temporal and all this type of stuff. Also age, age of the board is something that is real and we have not touched that. As the board becomes older and older, you will see more drifts, more deviations from the normalcy. And so what I'm getting at, it will help what we are trying to do, because we have these problems of time consuming and very costly. We are relying on transfer learning methods or domain adaptation methods to pretty much guess how this, if you would have an antenna here or place it there, how would you get what the difference would look like. So it's very much a effect.
So my first question is the synthetic signal generation is different system than the real signals?
Different system? No, it's the same system.
Same system environment, so essentially same resources as in memory and processors.
So just if I understand, it's can be the same board, and we have tried with this exact same board, and we have tried it with different boards, different Arduino boards, because that approach has been done in Arduino boards, but not different manufacturers, because it's kind of like an open hardware platform, so other manufacturers can create Arduinos. So we have not tried different manufacturers, and we have not tried different models. So it's exactly an Arduino Mega. So Atmel CPU, exactly the same type of CPU, exactly the same capacitors in the exact same location. So all the setup is exactly the same. It could be different boards. And I underline that because one of the applications of side channel analysis is for authentication purposes. Why? Because minute differences during the manufacturing process can act as a fingerprint. You need fingerprint for a device in terms of electromagnetic emanations. And a lot of people have tried to read the electromagnetic emanations to be able to authenticate or identify device A versus device B. So bottom line, we have tested against a wide range of the same model of Arduino devices, but not different models and not different manufacturers.
So in any case, like in the same system or different system, did you see such situation that because of memory or computation power, there is a lag in the synthetic signal or the real signal, and which will eventually lead to data mismatch?
A lag? What do you mean a lag?
Let's say you have a memory bottleneck. So for that case, your real data would not be produced as predicted by the synthetic. We have not observed that. You are correct to think like that. You are in the right track. The idea behind choosing Arduino device is because it has so simple architecture that typically you see exactly the same thing all over the time. Usually you see this type of stuff when more advanced microarchitectural features are supported by a CPU. Hash misses and bottlenecks and missing good speculations and being wrong on the speculations or reverting back to the previous state are all these features for advanced CPUs. And actually, this is something that we are going to try next. We are going to rely on an ARM Cortex M1, M2, M3, and 4 CPU architectures that have incrementally more and more features to observe this type of things. The idea is that we need to fingerprint the behavior, what happens if we have something like that, and then embed that to a gap. But to answer your question, no. And for our architecture, we do not expect to see this stuff. It was intentionally chosen to be very, very simple to disregard all these things. Yeah.
So just kind of dovetailing off of that, I'm curious about what could be the causes of the time drift that you're seeing. Just like whether you figured it out or just like some speculation.
We have some speculation here. We have
if you see, it starts great. But for some reason, and I think it has to do with the way the signals are being stitched right next to one next to another. If you see here, it starts drifting for a little bit, then a little bit more, then a little bit more, then a little bit more. So it's almost as if somewhere along the stitching process, we are injecting 2 or 3 extra samples. And then the 2 or 3 extra samples for every cycle become more and more and more. That's probably.
So it's kind of like a constant shift.
I think
that
yes,
builds over
yes.
over time of the simulation. Okay,
Yes,
awesome.
and that's what we observe here. And it's almost a constant shift. And as you will see, it's minor, very minor. And I believe it's totally reversible. And also if you switch to the frequency domain, this is not going to matter at all. Yeah, that's it. Thank you.
Have you done any exploration around different instruction sets? You're looking at the side chains on like to be able to, so like treating it as like a black box technology where not necessarily identifying anomaly, but you can be identifying what's the underlying hardware component.
Yeah,
What's the
hardware.
architecture, you know, is this ARM versus,
Yeah,
so
so-
RISC system, CISC system,
Yeah.
that type of
Granularity. Good question. We have not done that for that purpose that you're saying, but we have done that with the aim to reverse engineer, like disassembly. Or I don't know if it's disassembly is the right term, but figure out what the program is being executed inside the CPU without looking at the CPU. Like remotely have an antenna and figuring out that, you know what, it's not program A or program B, that I don't know if even have access to that, but it's this sequence of assembly instructions versus that. And we have not great success with that. It's close to 70% accuracy of instructions. Why? Because there are instructions that look very, very similar. Like we can do clusters. We actually have done that. We can do clusters of instructions that look almost identical. So yeah, we kind of dropped it, but I think that this is a very important direction, especially in the manufacturing realm where things are very close. And what we would like to do is not at the assembly level, but ladder logic. I don't know if you have heard. Ladder logic is the programming language. It's kind of like a graphical based language that people use to define what the PLC is going to do. It's called ladder logic. It's a standard. It's used by engineers extensively. So at that level, we believe we can do it. So higher level than assembly instructions, we believe that we can recreate and reverse engineer remotely via an antenna what PLC is executing.
So I have kind of a follow-up question within that, but building out your data sets where you have the sequence of instructions.
Yeah.
Is that looking at like the way it was numbered, it looked like it was just like first instruction, second instruction, third, second instruction, third instruction, third. Do you look at a more of a complete set of like first instruction, third instruction? First
Yeah.
instruction, fourth
So
instruction, and the signal.
what we actually try to do, but we didn't have a lot of time and resources to do it exhaustively. There are 123 instructions in the assembly, in the Arduino CPU. We tried, if we would create sequences of 2, it would be 123 to the power of 2. So it's a lot.
Yeah.
Immediately. So what we try to do is 1, 1, 1 to 2, 1, or 1 to 1, 2 to 1, 3 to 1, so on and so forth. We tried all possible combinations. At some point we said, okay, leave it. And we will, it's enough up to here. We will try to create a program with what is already there in the database. And that's what pretty much. Other questions? Okay, okie doke.